Now we're going to do a quick review over the graphical transformation rules. As a quick comment, it is helpful to know that most of these graphs can be sketched by creating a table of values. So you pick numbers for x, usually -2, -1, 0, 1, and 2, and you plug them into the function to find what the associated y values are. However, using the transformation rules is generally preferable because it'll take a lot less time to learn how the graph is shifting up, down, left to right, and how it's being stretched and flipped around. So here are the rules for what we call translations. They're usually referred to as shifts in a graph. So when you have something in the form f of x plus a number, this is going to shift that number of units up. So an example is having something like x squared. If you add a 2 outside of the function off to the side, then that's moving things up 2 units. Similarly, you could subtract a number and that would move it down that many units. Now, if instead of having the addition and subtraction after the function, if instead you have it attached to the x value itself, so usually it'll be inside of parentheses or inside of the square root or even absolute value bars, then that's going to switch it from being up or down motion and make it left or right motion. One word of caution on these are generally backwards from what you expect. And a good rule of thumb is that if you have things outside the parentheses, or if there aren't any parentheses, then that's going to be vertical motion. If there are parentheses or some sort of square root symbol, things inside of that will refer to left and right horizontal motion. So for our first example, we're going to use the function square root of x and then compare what happens when we are adding numbers in various places to it. So if the addition or subtraction is happening inside of the parentheses or inside of the square root symbol, like in this case, this is the left to right motion. Remember, it's backwards from what you expect, so this would be described as a shift left 3 units. This next one, the -4, is after the square root symbol. It's not inside of the square root, it's after it. So this is going to be vertical motion. This one goes the way people generally expect, so this will be down 4 units. And here's another subtraction, but this time it's gone back inside of the square root symbol. Remember, it's backwards, so this one will actually end up going to the right 1 unit. So these are described as our shifts. Now we're going to look at the reflections. You'll either be flipping a graph about the x-axis, which would be a vertical flip, because remember the x-axis goes left and right, or across the y-axis, which means it'll be a horizontal flip. It'll go from side to side. So for a reflection about the x-axis, just like our rules for shifts, if the negative is outside of the function symbol, whether it's parentheses or a square root symbol, whatever, then this is going to be your vertical motion. So it's going to flip the graph up and down. For a specific example, you could apply it to negative square root of x. For flipping the graph about the y-axis, which would flip the graph from side to side, this would be where you have the negative on the x inside of the parentheses or inside of the symbol operation like square root or absolute value bars. And in this case, that would be the square root of negative x for a specific example. But of course, you can apply this to other functions like x squared or x cubed also. Here's another example of what you would be doing on the assignment. They will tell you to work with a function like x squared, and then they'll give you something like a negative in front of it. So that's your reflection about the x-axis. Or they'll have the negative inside of the parentheses or inside of the function operation, and you'll say that that's a reflection about the y-axis instead. Now for the hardest set of transformations, we have the stretches and the shrinks. And again, these can be done either in the vertical direction or in the horizontal direction, depending on where the number is being multiplied or divided. So first, let's look at the vertical stretches and shrinks. If you have a number being multiplied by the entire function, so if your function's x squared, it would be something like having a 2 times the x squared. It will be a stretch if the absolute value of the number you're multiplying is bigger than 1. It will be a shrink if you take the absolute value of that number and it's less than 1. The fact that we use the absolute value symbol here is really just to separate the reflections from the stretches and shrinks. So you can just ignore the negative sign. If you're seeing a whole number like 2, 3, or 4, it's going to make it 2, 3, or 4 times taller. If it's a fraction like 1/2, then it's making it half as tall. And we describe that as a shrink instead then. For the horizontal motion, this one is confusing because it's described based on what we are dividing x by. So again, this will be directly applied to the x variable, so it'll be inside of whatever brackets or symbols that you have in the function. So this one's going to be a stretch if the absolute value of c is greater than 1, just like above, and it'll be a shrink if the number is less than 1. What's tricky here is that we're describing it based on what x is being divided by instead of what x is being multiplied by. So for an example, if you have x divided by 2, then that means our c value is 2. So it is a stretch by a factor of 2. Usually people look at this and think, oh, it's cutting x in half, so it's making it half as wide, but it's backwards. It's actually making it twice as wide. The other thing that makes these confusing is that sometimes they don't write it as x divided by a number. They write it as a number being multiplied by x, in which case my recommendation to you is to take the reciprocal of the number you see that is multiplied by the x. Then you can just use that reciprocal value for determining if it's going to be a stretch or a shrink instead. These operations are a bit trickier, so I want to go a little more carefully through each of the answers I have here. This time I'm applying the transformations to the function square root of x. So if it's outside of that function symbol or the parentheses, then that should be the vertical motion, which you can see in these first two examples. These are pretty straightforward. If the absolute value of that number is bigger than 1, then you will say it's a stretch by that amount. If it's a fraction or a decimal between 0 and 1, then you will say it's a shrink by that amount. The horizontal motion is the trickier one. So if it's written as a fraction, then you're just using whatever is in the denominator. And since this number is bigger than 1, this is causing a stretch of the graph. Although you might be tempted to think that it should be a third as wide. It's the opposite. It's going to make it 3 times wider. For the cases where you have a number being multiplied inside of the symbol, like I said, this is a little bit tricky because you might want to use the reciprocal of that value instead. Think of this as dividing by 1/2, which means my C value is 1/2, and since the absolute value of that number is less than 1, we call that a shrink. And again, this is inside of the square root symbol, so it's the horizontal shrink instead of the vertical shrink. Okay, so we've talked about how to look at a function and state whether it's going to be shifted up or down, left or right, whether it's going to be reflected or stretched or shrunk. But now let's actually apply that to sketching some of the graphs on our own. The first thing you'll want to do is identify what the parent function is. And this is generally done by ignoring any of the constant numbers you see. If there are numbers being multiplied or added or negative symbols in there, try to tune all of those out and just focus on what you have. Is it a square root? Is it an x squared? Is it an x cubed or an absolute value, etc.? Once you've identified the parent function, then you can start going back and looking at the numbers that are being multiplied and added. The vertical motion, remember, will generally be outside of the parentheses. I usually like to do that stretching and shrinking first and then do the shifting up or down. And then I separately go in and I consider the horizontal motion as its own separate component. So then I look at what's happening inside of the symbol. I apply the stretches and shrinks first, and then I apply any of these shifting left or right. So it's kind of like the PEMDAS order. You do your multiplying and dividing before you do your adding and subtracting, but you want to do the vertical and the horizontal separately. So now let's look at drawing some of those sketches by hand. I've gone ahead and drawn in with a black marker what the parent function would look like without any of the transformations, just in case you're unfamiliar with these shapes. So first, if I ignore the +1 and the -2, this is the x squared function. I'm just focusing on the parent function for a second. That's where this shape comes from. Then I'm going to look through and say, okay, well, I know that this graph needs to be shifted to the left once and down twice. So basically I could pick a dot like here at the origin and go left 1 and then down 2, and I could draw that dot there instead. And then you could pick another dot on the graph, like there should be a coordinate here at 1, 1. It's going to go left 1 and down 2. And you could just pick a few points like that, but really you're just trying to get the basic shape that it's this U-shaped graph shifted left and down. Okay, next I have the x cubed graph, but the transformation here is I need to do a reflection, and this is a vertical reflection, although I will mention that this graph is weird because the vertical and the horizontal shift actually ends up looking the same either way. But the way I've written it, I did not put the parentheses with the negative inside, so I'm going to do this as a vertical reflection. So basically you want to take the entire shape and imagine flipping everything about the x-axis, which is here going left to right horizontally. So I'm flipping everything upside down. So instead of going down here, it's going to be up on the left-hand side, and then it's going to come through and go down on the right-hand side. And for our last parent function, we have the absolute value bar, which kind of looks like a V. This one needs to be stretched vertically by a factor of 3, and this can be a little bit hard to show when you're sketching freehand. It's a little bit easier to do when you have very precise points to work with. And I need to shift things to the right by a factor of 2. So remember that this is backwards from what people usually expect. So first, let's start with shifting to the right 2 units. because my point that's usually at the origin is still going to be there on that height of 0. Multiplying the height by 3 does not affect anything. But then what's going to happen, instead of going from that point and going right 1, up 1, it's going to go right 1, up 3. That's how we demonstrate the vertical stretching shape. So it's kind of like it's making the slope steeper. So I just need to make this a sharper V essentially. And then the same thing would happen on the left. Instead of it going left 1 unit, up 1 unit, now it's going to go left 1 unit, up 3 units. So again, it's just going to be a sharper V shape. So this would be a stretched by a factor of 3 and shifted to the right 2 units shape. Hopefully that will be a good quick review of the transformation rules so that we can apply them to some other functions coming up over the next couple weeks.